Okay, I think now we can start today's discussion. So, welcome everyone. Thanks for joining. Uh, today is the 11th week of our discussion session on this course, Basic Analysis, offered by Professor I. Kirana. So, in today's session, we will be discussing a few questions on norms. In particular, I will be solving the assignment number 10, I think so, uh, from the uh, from the course webpage. And I've added a few more questions. So let's see if time permits, I will also solve those. So without a further delay, we can start. So let me introduce myself formally. So I am Prerak from Hopal, and I conduct these live discussion with you guys each Monday, 7 to 9. This is another one such session. You can find all these recordings of our discussions on this YouTube channel. Uh, my YouTube channel named as Maths with Prerak. You can search it in on the YouTube search bar, and you will get the channel recommendation in the searches. This recording as well will be uploaded on the same YouTube channel by tomorrow morning. And if you are watching this video on YouTube, and if you find any difficulty understanding any argument, you can comment it uh, below the video. I will try my best to resolve your doubt as soon as possible. Okay, so if we are all set, so let's begin with today's discussion. Let's discuss some questions. So question number one, for p greater than 0, define the function norm p from Rn to close 0 to open infinity as norm of p defined to be the summation, finite summation from 1 to n of xi, modulus of xi to the power p, and taking the pth root of that quantity for all x in Rn. Now it is asked that which of the statement is true. So is it the first one where the norm is where this defines a norm, this function defines a norm for all p greater than equal to greater than 0, and this function defines a norm if p is greater than 0, sorry, p is greater than 1. This defines a norm if and only if p is greater than or equal to 1, or none of the above. Okay, so we will try to see why, uh, when will it define the norm and when will it not define the norm. So clearly you can see from these options that this function defines a norm completely depends on the value of p you choose. Okay, um, so the point here is that, so today what we will prove that c is true. Okay, so in particular when p is lying between 0 and 1, the above function must not give us a norm. Okay, this is not a norm. So how do we say this is not a norm when p is between 0 to 1? We need to come up with an example. Okay, so uh, we need to we need to come up with an example which doesn't satisfy the norm property when we take p varying from 0 to 1. Okay, so this is how we will prove that this statement is false. Okay, and now why the second statement is false? Second statement is not false because uh, this function is a norm when p is greater than 1, but it's not the complete truth. Okay, so it is partially true, whereas the statement c is completely true. You cannot have norm uh, when p is between 0 and 1. So that's what c refers to. That's why the statement e is completely true. Okay, so we will see. So in order to prove why the first statement is false, we need to give an example Okay, and we will prove the C part, correct? Okay, let's move on to proving this. So before proving this, let us recall the definition of the norm. Okay, so we say a function. So we say a function f, or yeah, let's say write it as f from Rn to this is a norm if number one, that f of x is 0 if and only if x is 0. Okay, here my x is a vector. In particular, it has n coordinates. Second is, yeah, second is it satisfies the triangle inequality. Okay, so that's these are the two property, and the third property is that f of alpha x, where alpha is an scalar in R, is equal to modulus of alpha times x. So in some sense it is linear, uh, but the modulus comes out, not the exact scalar comes out. So where alpha for any alpha in R. Okay. Second statement is true for all x and y vector in Rn. Okay. The first statement is also true for all vector x in Rn. Okay. So uh, this is the definition of a norm. And how do we translate this definition in our case? So in our case, if you want to translate this definition, so let me write it here itself. So we will say that this is a norm. Okay, this defines a norm if is equal to 0, if and only if the vector is 0. Similarly, the triangle inequality in that norm holds. Okay, and it is linear. Okay, so I have written for our specific case what this definition of what this function uh, needs to satisfy. Okay, so in red you need to in the red I've written down the statement. The function need to satisfy to this particular function, it needs to satisfy to be called as a norm. Okay, so let's see. So so first of all, we have defined a function which is like this. Okay, so it means that this function is already finite. In other words, since it is taking a value, if I apply x in this, I am getting a value in this positive uh, real axis, correct? So in some sense, yeah. So in some sense, I'm saying that the value it is taking is finite. which is equivalent to say that this is finite. Okay. So uh, yeah, we don't need to check for the finiteness of the norm. It is already defined to be the finite function. So that's out of the scope. Yeah, so we don't need to check. Okay. Okay. So now let's move on to prove us to see whether we will find difficulty proving the uh, property. Okay. So in our case, I'm starting with p to be greater than zero without any condition. So and let's see how far we can go proving the properties of norm. So what the first property? We need to say that norm of x is zero if and only if vector is zero. Okay. So yeah. So if I start with norm of x to be zero, then this implies that summation of some positive quantity. So it is equivalent to say that norm of p to the power p is also equal to zero, because 0 to the power anything is 0. Okay, so I am safe to say this as well. Now, what does this imply? This is equivalent to say that this is equal to 0. So this finite sum of positive number is equal to 0. But can finite sum of positive number, okay, be equal to 0? They can only be equal to 0 if and only if. So this is also if and only if each of xi is equal to 0 for all I. Okay. So in other words, when all of xi's are 0, it is equal to saying that x vector is equal to 0 vector. Okay. So this is an equivalent statement. So at each step I'm having a y equivalence. So if you start with the last step, with assuming that x is equal to 0 vector, you can just trace your argument back to the first step where we started. Okay. And if you start with the very first step, you can come back to the you can come back to the step that x is a 0 vector. Okay. Any questions? Okay. So if there is no question, we can move ahead and prove the next part. So in part two, okay. So in part two, we have to prove the triangle inequality. So let me skip that part for now. Okay. Let's prove the third property first. Okay. So I'm skipping two. Okay. Skipping two. Yeah. So what is the third property? Third property says it's linear in some sense, that the modulus of a scalar comes out from the norm. So alpha times x, norm of this, is equal to norm of alpha times this for any alpha in R. Okay. So now if I uh, think of this, I just need to use the definition. So what is the definition of the norm? It is just summation I varying from 1 to n x I norm of this to the power p whole to the power 1 over p. So just a quick recall here. Whenever I scalar multiply, whenever I multiply scalar to a vector, uh, it gets multiplied to each of its component, each of its coordinate. So in particular, it will be this. Okay. So now the new coordinates will be, the new coordinates will be alpha times x1, alpha times x2, and alpha times x1. Okay. So that's what is happening. Um, yeah. So I will get that. And now this is whatever I am having on the right hand side. I use this fact. Uh, so this is the first fact. Second fact is modulus of two scalars. Okay. So here xi is again an scalar. It's real number. And modulus of two real numbers is equal to multiplication of their modulus, individual modulus. Okay. So that's what I'm going to use uh, in the right hand expression. So I will get summation I from 1 to n, summation I from 1 to n, alpha mod xi, power to the power p, and then whole power over p. Now this power also distribute. Okay, so if you have alpha beta to the power p, it distributes among these scalars. So that's what I'm using here. So it distributes alpha to the power p, and you can also notice that alpha is a common among the summations. Okay, so you can take this alpha to the power p out from the summation from this finite sum. Okay, and whole to the power 1 over p. Now once you take out this alpha mod alpha to the power p outside this bracket, uh, it will has to face this 1 over p power. So, and when you take the pth root of this alpha to the power p, you get 1. Okay, so this will cancel out. So it will be 1. And what is remaining is actually this, which is nothing but, so this term is nothing but norm of x, pth norm of x. So what you get is mod alpha times this. So the third property is also satisfied. And you can notice that I'm not changing, I'm not taking any cases on p. So in both of the cases p was positive only. Okay, in order to prove this also p was positive, and in order to prove the uh, linearity of the norm, p was positive. Okay, there was no condition on p. So when do we have problem? So so when do we will have problem? So idea here is that we will have problem when we will have when we consider the uh, property number 2, which we skipped. Okay, so now let's move on to property number 2. So in property number 2, we need to prove uh, triangles inequality. Okay, so what is that? So it is norm of x plus norm of y is less than or equal to norm of x plus norm of y. Okay, now uh, here I break it into two cases. So case number 1, when p is larger than 0 but smaller than 1. So that's our first case. So in this case, I'm saying the statement will not hold. So it will be false. And what is an example? So whenever I say that something is false, I need to come up with an example. So what is the example that I'm giving in this case? So in this case, uh, consider this example. Take point x to be 0, 1, comma 0. Okay. First of all, take n to be 2. Okay. Fix n equal to 2. So basically you are working with vectors in R2. Okay. Now you take x to be 1, comma 1, 1, comma 0, and take y vector to be 0, comma 1. So in particular, these are the unit vectors in the independent directions. And now x plus y is a 1, comma 1 vector. Okay. And the norm of x plus y, the pth norm of x plus y, is actually 1 to the power p plus 1 to the power p, and this whole to the power 1 over p. So which is going to be 2 plus 1 over p. Correct? And what is the norm of x? Norm of x is just 1 to the power p plus 0 whole to the power 1 over p. So it will be just 1. Similarly, norm of y is also equal to 1. Yeah. And now, yeah. And now, if the inequality is satisfied, we will get we need to get this kind of, if this inequality is satisfied, we need to end up with this relation. This relation needs to be satisfied. But if you look closer and if you try to uh, write down the right hand side of this inequality, you will get 2 to the power 2 to the power 1 over p, and on the right hand side you get 1 plus 1, which is going to give you 2. Okay, with this relation that 2 is smaller, 2 to the power 1 over p is smaller than 2. Okay, now I will prove that this particular inequality is wrong. Why this particular inequality is wrong? Why? Because look at this part. P is smaller than 1, okay, and larger than 0, which implies that 1 over p is larger than 1. Okay, which implies that 1 over p is larger than 1. So you think of p as 1 over p as q, and something, and 2 to the power, and 2 must be smaller than 2 to the power q. Okay, because exponential is an increasing function. So if you are starting with increase in value, okay, so you must be able to get the, since exponential is an increasing function, that's why this will hold. And what is my function in that case? My function is a going to a to the power x. Okay, so you can define a function, sorry, you can define a function from x going to a to the power x. Okay, so this is from r positive to r positive for a greater than 0. If you define this function is increasing. Okay, so if this function is increasing, or in particular you need to take 1 to infinity, that's better. So we only need to consider this case. So this function is increasing. Okay, so that's why you will get this inequality will not be satisfied. So you will come up with, so you have get a contradiction over here. So this is a contradiction. So a contradiction. So you have arrived to a contradiction. That means the assumption that you made earlier, that if P is lying between 1 to 0 and this inequality is satisfied, is wrong. Okay. So that's the mistake. Uh, that's the wrong assumption that we have made earlier. Okay. Is everything fine at this moment? Okay. So now let's discuss the case 2. So case 2 is when P is greater than 1. Okay. So in this case, again, we need to prove the triangle inequality. Okay. Uh, so we start with this fact. So here we will use something which is called Holder's inequality. Okay. And I know that Holder's inequality has been discussed in the lecture notes. So I will be directly using that as a fact in my solution. So if I start with x plus y, p norm to the power, okay, so let me say this way. So if I start with okay, so what is x plus y to the power p? It is summation of xi plus yi to the power p, and then pth root of the summation of the sum. I is varying from 1 to n. Okay. So now I let me take this part which is inside of this bigger bracket. Okay. So let me first find the bound on this quantity, and then we will uh, get the norm. Okay. Then we will get the inequality of the norm. Okay. So let's do that. So we start with this part, summation xi plus yi to the power p, I varying from 1 to n. Now this interior bracket can be written as like this. Okay, one can break it into this way. Um, and yeah, there is one more step that I missed. It's not just the bracket; it is the sum. It is the modulus of the sum. Okay, so it's the modulus of the sum. It's not just the simple vector. It is the modulus of the sum. So it is basically modulus of this times modulus to the power p minus 1. Okay. So now if I look into this quantity, let me zoom a bit. So it will be, yeah. Okay. So if I look at this part, now, because these are just a real number for a fixed I, at each I, it is just a real number, sum of real numbers, and getting and finding out the absolute value. So we already have a triangle inequality in this case. Okay, so the idea is to use that triangle inequality. So in particular, I am using this fact that xi plus yi, this modulus is smaller than or equal to this. Okay, so I'm using this fact to get this inequality. Okay, yeah. Now once we get this inequality, the idea here is to use the Holder's uh, inequality. So how do we go to the Holder's inequality part? So for that Holder's inequality, you need to have first of all summation over, yeah. So something like summation over ai bi, and you find the bound over it. this is smaller than the pth norm on A, P uh, times the qth norm on B, where this P and Q satisfy this relation. Okay. So we want to use this inequality twice. So how do we use it? So first, we will consider this summation. We will treat the first term as A and the second term as B. Okay, and apply, sorry, as AI and BI, and apply this result. Okay. Similarly, for the second case, we will consider this as AI and this as BI, and we apply the Holder's inequality. Okay. So that's the idea. Okay. So now let's apply the Holder's inequality and let's see what do we get. So let me write what I had on the right hand side because it's going to be important. Uh, Summation xi yi to the power p. That was on the left hand side, and this was smaller than summation xi to the power xi times xi plus yi to the power p minus 1, I varying from 1 to n, plus summation yi xi plus yi to the power p minus 1, I varying from 1 to n. Okay, so this is what I had on the right hand side. Now I apply the Holder's inequality, or do I get this will be then smaller than the summation xi power p going from 1 to n whole power 1 over p, okay, times summation I from 1 to n xi plus yi to the power q times 1 minus p whole to the power 1 over q plus summation I from 1 to n yi to the power p whole power 1 over p times I going from 1 to n xi plus yi to the power p minus 1 times q 1 over q. Okay, now here are some facts that uh, q times 1 over 1 minus p, q times 1 minus p is equal to, so it is equal to, let me uh, write in this way, this is equal to 1, and now p plus q, okay, divided by is equal to pq in particular, and now this is what we get from here, and now uh, so p is equal to q minus q. So if I take q out, I get um, yeah, I have p minus 1 over here, not yeah, so there was a mistake. So I will get p minus 1, correct, is equal to p. So I replace this into the equation, and I will get, so this will be replaced to P. Similarly, this will be replaced to P. Okay. So now what is the idea is to divide this part. Okay. Divide this part. Which part? This part in particular. Divide this part both sides. So as you can clearly see, if you do that, if you divide this part both sides, on the right hand side, what is left is just this norm of x, pth norm of x, and pth norm of y, correct? But what on the right hand side, what is left is the same quantity, this I from 1 to n, xi plus yi to the power p, 1 minus 1 over q. Okay. And now 1 minus 1 over q is equal to 1 over p. So it is equal to 1 over p. And now what is this? This quantity is equivalent to, the right hand side is now the x plus y p norm, which is smaller than xp plus y. Okay, so in particular, we have proved the uh, triangle inequality for the case when p is greater than 1. Okay, now you may ask, you may ask, why can't we apply this Holder's inequality in the case when p is between 0 and 1? So the answer is simple. Answer is because you don't have Holder's inequality for that dimension. Okay, so you don't have a Holder's inequality in that dimension. That's why you cannot apply. Okay, so yeah, and we have already seen that there is no way because there are contradictions. So this inequality doesn't hold in the case when p is from 0 to 1. So that is not true. And for p greater than 1, we can use Holder's inequality to prove, to get the triangle inequality for p norm. Any question? Okay, so if there are no more questions, we can, I think, move ahead uh, and discuss this question number 2. So in this question, we need to state whether it is true or false. Okay. So if a sequence xn is, if xn is a sequence in Rn and x belongs to Rn, such that the limit under the infinity norm or the supremum norm is zero is yeah, xn converges to x under the supremum norm, then the question is, does xk also converges to x under the p norm? Okay, so that is the question. And so what do you guys guess? What should be the answer? So this question requires an observation from the previous discussion we had. Okay, so in one of the question we had we had find out we found out uh, a bound on these norms, in particular the relation between the supremum norms. Okay, so the idea is to use those uh, use that relation. Yeah. Okay, so okay, yeah, I remember now. We have proved for p equal to 2 case, but what about the general case bound? Does the bound in the general case also happens to be true? And the answer is yes, it does happens to be true. Here is a typo. It is x in Rn. Okay, so uh, first I will show you uh, the bound that I'm talk of what I'm talking about, and then we will prove the this result. Okay, so in the last session, we have discussed this bound that x2 uh, 2 norm of any vector in Rn is smaller than the uh, square root of n times the supremum norm of that vector. Okay, so this is what we have seen in the last session, in the last discussion session. Okay, but can we generalize this relation to the higher dimension? Oh, sorry. Can we generalize this to the higher for higher p also? Okay. So again, the proof goes as straight as the last time. There is no difference in the proof. Okay. And yes, it can be further generalized to any norm p. So in particular, my claim is that does this hold? Okay. Um, so the idea is again similar. Um, so let me just rewrite the definition of the supremum norm. Okay, since it is just the maximum of all the from the finite quantities, so one of the quantity must attain that maximum. So let's say uh, k is the one for some k sitting between 1 and n. Okay, so now this infinity norm is equal to mod of k. Now what is the p norm? P norm is nothing but summation of mod uh, summation of mod of xi to the power p from 1 to n, where I varies from 1 to n, and taking the pth root of this sum. Now clearly this quantity will be smaller than the maximum of all those xi's. Okay, so in particular I will take it to be xk, okay, from 1 to n and 1 over p. Now since this is a constant, the for because it is not dependent, this xk is not dependent on I. So it is just I'm adding constant. How many times I'm adding constant? Uh, Almost n times. I'm adding constant n times. So here is, yeah. So what will I get? out of that is this quantity will be equal to taking the xk out, xk to the power p and whole to the power 1 over p, and the summation of 1 from 1 to n to the power 1 over p. So in particular, you will get the infinity norm times the pth root of n. Okay, so this will be the bound on xp. So you will have this relation for any p greater than or equal to 1. Correct. So in the claim I made a mistake. It is not the square root of n, it is the nth root of, sorry, pth root of n. Okay, everything else is fine. So now the idea is to use this uh, bound relation between the pth norm and the supremum norm to solve the to solve this question. Okay, so is this fine? Okay. Uh, so now in the question it is given, it is asked that if a sequence is convergent to uh, sequence xk for k in n, convergent to some x in r under the supremum norm. Okay, so does or will it also converge under the p norm? Okay, so let me just rewrite the definition of the convergence. So when do we say something is, if when do we say xn converges to x? If for epsilon greater than 0, for any epsilon greater than 0, there exists some delta. Okay, in this case, there exists some n depending on the epsilon in natural number, such that xk minus x under the supremum norm is smaller than epsilon for all k larger than or equal to n epsilon. Okay. Okay. So since it is true for any epsilon, I take for very specific epsilon. I use this. This is given to me. Okay, this is given to me. So for any epsilon, I will have some n epsilon. So I take for epsilon to be smaller. Epsilon I take for epsilon by, okay, so epsilon by the nth root. Sorry, pth root of n. So this is again a positive quantity. Okay. So for this value, I will also, there will exist some n. Let me call this to be epsilon prime. Okay, for simplicity, there will exist some n, some natural number, such that xk minus x supremum under supremum norm, this will be smaller than epsilon prime for all k larger than n epsilon prime. Okay. Okay. Now, what do I need to prove is that for given epsilon, I need to find out some. I need to find some natural number, so that xk minus x under the pth norm is smaller than that epsilon. Okay. So I'm starting with any epsilon. Yeah. So I'm starting with uh, let epsilon be positive. Okay. And then I need to say that this is smaller than epsilon. But this quantity, I know that this quantity is smaller than nth root of, sorry, pth root of n times the supremum norm of the same number. Okay, and for this infinity norm, I can work with this epsilon, okay, which is given. I can work with this epsilon prime and find a natural number which is n epsilon prime to get a bound in terms of epsilon prime. Okay, so this will be smaller than epsilon prime for all k larger than n epsilon prime. Okay, now what is epsilon prime? Epsilon prime is in particular epsilon divided by the pth root. So that's why I have chosen this uh, epsilon prime carefully, so that it will cancel out the extra factor. Okay, so it cancels out that, and what do you get is epsilon only. So in particular, you have found out. So in particular, what you have done. So in particular, xk minus x pth norm of this is smaller than epsilon for all k bigger than n epsilon prime. Okay, so this is important, this is not important. So this epsilon and epsilon prime is not important. So sorry, it is important, but the only important part is that it is a natural number. So for this epsilon, and since your choice was arbitrary, so you can write that for any epsilon there exists an epsilon prime uh, in natural number such that this happens. Okay, which is equivalent to say that this norm p norm is tending to 0, uh, yeah, as k tends to infinity. So this is what we were asked to prove. If under supreme norm something is a sequence is converging, then will it converge under the p norm as well? And it is in particular happens to be true, and we have proved this. So this is the proof of that part. Any questions? Okay, if there are no question, we can move ahead and discuss the uh, next question. Now this question is involves the sequence of functions. Okay, so again it is a true and false type question. We have given a sequence of functions such that the sequence of functions converges to the zero functions for all x. That means it is a point-wise convergence given. Now it is asked that whether this sequence of functions will converge uniformly to the zero functions. Zero function. Okay. So generally something is point-wise will not be true uh, in the uniform, will not imply the uniform convergence. Okay, and this is an example for that. So if you start with something, so this statement is in particularly false, and in order to say why it is false, we need to give an example of a pointwise converging sequence of function to zero function that does not, so it converges pointwise but doesn't converge uniformly. So that's the example we need to give. And the example we will take is a bit simple. We will take a simpler example. Yeah. So consider this example, uh, fnx, which is defined to be um, x when it is, let me write it better. So it is defined to be 0 when x is smaller than or equal to 0. It is defined to be x when it is between 0 and 1 over n. Okay. It is defined to be 1 over n when it is larger than or equal to 1 over n. Okay. So this function is continuous. So if you try to draw for any given uh, n, okay. So first of all, it is a sequence of functions. Is that clear? Because this n is varying in the natural numbers. Okay. So notice that fn is a sequence of functions. Okay. What does it mean? That it means for each n in n, there is a function fn from R to R. Okay. And second of all, each fn is continuous. Okay. And simpler way to understand the continuity of this function is to just draw this function. You can see that if you draw this function, it is like this. So up to 0, it is just on the axis. Okay. And between 1 over n to 0, it is like the straight line. Okay. As soon as it hits 1 over n comma 1 over n point, it becomes a constant function again. Okay, so that's a constant, that's a continuous function. You can also prove using epsilon delta definition. uh, yeah. So or you can say that it is in in three intervals it is continuous, and uh, at the point of intersection of those three intervals, it is continuous. Okay, basically these are the 2 points. This is the first point, this is the second point. It is given to be continuous, so it is a continuous function overall. So there is nothing uh, fancy about that part, about the continuity of the function. So it is a continuous function. So it is a sequence of continuous functions. Okay, so that part must be clear. Now, first part we need to say that it is point-wise. Uh, so it is point-wise convergent to zero function. Okay, so what do we mean by that? First of all, so point-wise convergent. If you fix your x in R, okay, so and you consider this sequence, so this becomes a sequence in real number. So, so this becomes a sequence in real number. Okay, because each of its entry is a real number, so it becomes a sequence in real number. And now you know how to deal with uh, 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 a sequence of real number. We know the convergence of limit. We know the convergence of the sequences of real numbers. So we use that definition. So in particular, if we for any epsilon greater than 0, we need to find out there exists n in natural numbers such that fn x needs to be, and since we are comparing with the 0 function, so which at each point is 0, so the limit of this sequence must be 0 for all n greater than equal to n. Okay, that's the definition of the convergence of a real number sequence. Now, does it satisfies over here? So if I start with any epsilon, okay, if I start with any epsilon, I can find out a natural number n such that 1 over n is smaller than that epsilon. Okay. Okay, so I can always find out such n such that 1 over n will be smaller than that epsilon. Okay. And if this happens to be true, then the first thing, second thing is that 1 over n for any n larger than this n. If I take any n which is larger than this n, 1 over n, 1 over small n will also be smaller than 1 over capital N. Okay, so these two things will happen, and these are the two things we need to uh, happen. We need to satisfy. So now, if I take any point x in R, okay, so since we have fixed a point in R, so yeah, so since we have fixed a point in R, so we know by definition that Fn, now by this definition we know that Fn x will always be smaller than or equal to 1 over n, correct? It will always be smaller than or equal to 1 over n, because if x is lying below 0, then it is 0, function is 0, so it is uh, smaller than 1 over n. If x is lying between 0 and 1 over n, then it is again smaller than or equal to 1 over n, and if it is above 1 over n, it is again, it is equal to 1 over n. So so in each case, in each interval, it is smaller than or equal to 1 over n. So now we just use that fact to say, so I just use this fact to say that ff of fn x, this is smaller than 1 over n, okay, in particular 1 over n, capital N, in particular smaller than epsilon, okay. So yeah, so this implies that fn x converges to 0, and this whole proof, this whole part is independent of the choice of x, okay. So uh, we can say that it is pointwise convergent to a zero function, okay. Any question? Okay, so now the next part is to show that it is not uniformly convergent to zero function. Yeah, so how do we say that? For in order to say that it is not, so what is a uniformly convergent convergence? First, let's see that. So if you consider a function sequence fn, okay, it is said to be convergent uniformly to f if for any epsilon there exists n depending only on the epsilon greater than 0, sorry, in natural numbers, such that fn of x minus fx is smaller than epsilon for all Oh, okay. So what was the question again? Yeah, I think uh, okay. Yeah, but in this case, okay, I've started with the wrong example, I think so. Yeah, because in this case, yeah, yeah, yeah. So this is actually point-wise convergent to zero, as well as it is also uniformly convergent because this. Yeah. So let me first write down the definition of uniform convergent, then I will say that what is the mistake that I have made. That I have started with the wrong example to work with. Okay. So this fnx minus fx smaller than zero for all, yeah, for
For all
all
x.
n greater than equal to an epsilon and for all x in R. Okay, so in our case, this is actually happening because if I start with an epsilon, I can come up with an n in natural number such that 1 over n is smaller than epsilon. Okay, so this 1 over this n does not depend on the choice of x that I'm taking. Okay, so this will always smaller than 1 over n, which is always smaller than 1 over n, which is smaller than epsilon. So in particular, this is a uniform convergent. Okay, so the last proof itself give you the uniform convergence. Okay, so this is not an example. Okay, so I have given a wrong example. So this is not an example which says that this statement will be false. It is an example which supports that it will be true. So, but this question, this statement is false. Okay. So I don't know the example yet of this. Then, uh, if something, if I will, I will discuss then this question in the next discussion session. Okay, instead of this discussion session. I'm sorry about that part.
Actually,
Okay, but if you know any example which is
x,
point-wise convergent, but it is not uniformly convergent to zero, you can uh, let me know.
yes, x power n is a sequence of functions which is defined on a, uh, uh, open interval 0 comma 1. I mean semi-open interval 0 comma 1.
Okay.
One is
Yeah. So the example that I'm giving is not the correct one because it is also it turns out to be it is also uniformly convergent to zero function. So it is not the correct example. Okay. So leaving that part, I will discuss the example in the next discussion session. Okay.
no x
Is
power
it
n.
fine?
No, x power n, which is defined on a semi-open interval 0 comma 1, which is a point-wise convergence but not uniformly convergent.
Okay. So
So since the limit function, which is not continuous, but all other terms are continuous functions.
yeah. So in particular, this question number 4. In this question number 4, yeah. So in this question number 4, I have given a function. There exists a function uh, f such that f is differentiable, f prime is bounded, and f is not uniformly continuous. Okay, so you need to say whether this statement is true or false, and this statement is apparently false. And how do we prove that it is false? So we will prove that by saying because it is by saying that saying that if I start with this assumption that f is a function with which is differentiable everywhere and its differential is bounded, uh, then f is uniformly continuous. Okay, so we will prove the falseness of this statement by proving that if f from R to R is differentiable everywhere and f prime is bounded, then f is f is uniformly continuous. Okay, so we will prove this fact, and since this fact will be true, so this statement is false. Okay, is this clear? Yeah. Okay, so the idea here is to use mean value theorem, and I assume that you are already familiar with the statement of mean value theorem. So I'm going to state the mean value theorem anyway. Uh, so uh, yeah, so uniformly continuous. Again, it is continuous on a closed interval, uh, and that interval, uh, and for any given epsilon, there exists a delta, and this delta doesn't depend on the choice of a point where you are proving the continuity. It is independent of the point you are proving continuity. Okay, so it is basically uh, continuous for over all over the interval. Okay, so delta only depends on the epsilon, choice of epsilon. So that's what the uniform continuity is. Okay, so let me start with two arbitrary points on R. So let x and y be 2 points in R. Okay, now consider their close interval x comma y. So it is in a subset in R, correct? And further notice that f, now f can be think of as a function from xy to R because it is a function on a bigger domain. So you can restrict your function to this smaller domain, smaller close interval. Okay, and further uh, let k bounds f prime. Okay, that is f prime modulus of that is smaller than equal to k. Okay, so now the idea is to apply uh, mean value theorem. So the idea here is to apply mean value theorem for the function f from xy to R. Uh, okay, so the statement says that as follows, that let f be a function from a closed interval to R, uh, a differentiable function, then there exists um there exists there exists a real number c in the interval x comma y such that f prime of c, okay, attains the average of this number. Okay, average of the function in that domain. So it is basically this f prime is equal to this. Yeah, so that's the mean value theorem. So we are going to use this fact to prove the uniform continuity. Okay, so now so applying this theorem, you get a c in the closed interval x comma y such that this inequality is satisfied. Now you take modulus both sides. Okay, what do you get? So if you take modulus both sides, you get this. Okay, now modulus can be broken into the into the denominator and numerator. So that's what I do. It will still give you the same quantity. Okay, so that's what you get. And now this further implies that f prime of c times x minus y is equal to fx minus fy. Okay. Now this quantity, this differential bound on this different, the modulus of differential is. So let me further rearrange the equation. This is equal to f prime of c modulus times y minus x or x minus y, whatever, however we would like to write it. Now this quantity, we know it is smaller than k. Okay, so we use that bound to say that. Okay, so this is smaller than this quantity. So in particular, what you have obtained is this. So let me square it up. Okay, put it in a nice box. Now we come back to the uniform continuity part. So for uniform continuity, let epsilon be a positive real number. Okay, and choose your delta, which is completely dependent on epsilon, to be epsilon by k. Okay, choose your delta to be epsilon by k, where this k is the bound on the differential. Okay, so you choose your delta epsilon, which is epsilon to be epsilon by k. Then from the previous box, okay, if I just go back to that previous inequality that I obtained, so what do we have? We have xy minus fx. This modulus is smaller than k times xy minus y. So whenever my distance between x and y is smaller than delta epsilon, then distance between fx and fy will be smaller than k times delta epsilon. Okay. Now what is delta epsilon? Delta epsilon is actually epsilon by k. So what do I get is, and now k cancels out. So in particular, what do I get is fx minus fy is smaller than epsilon. Okay. Is smaller than epsilon. So does this complete the proof? Yes, it does, because we have started with the epsilon. We have for this epsilon we have delta, which is completely dependent on epsilon, and whenever this distance of xy is between the this delta neighborhood, okay, your fx and fy will be smaller than epsilon. Okay, so yeah, so this is equivalent to say that f is uniformly continuous on R. Okay, this completes the proof of this statement. Is this fine? Okay, so let's move on to discuss the uh, question number 5. Let me just have a quick look. Okay, so we have three more questions to discuss. So let me start with this. Um, yeah. Question number 5. So we have fn be a Riemann integrable functions for all n in natural number, and let f be a Riemann integrable such that fn converges to f uniformly on AB. Then you need to prove that the integral value of integrating fn over AB converges to integral value of f after integrating over AB. Okay, so first of all, you can notice here that once you integrate your fn over an interval, you get a real number. Okay, so if you consider this integral, this is a real number sequence. Okay, this is a real number sequence, and now this real number sequence, it is asked now that this real number sequence converges to this real number as n tends to infinity. So this is what does this state, this symbol means. Okay, so these small things are important for your own understanding of the subject. That's why I'm mentioning it separately. Okay, so we start with now let's see what is given to us. So we have given these things, that each fn is a Riemann integrable function on AB. Okay, further f is also a Riemann integrable function on AB. Number one. Number two. Number three, fn converges to f uniformly. Fn converges to f uniformly. Okay. Yeah. So now, so we want to prove. So let me start with let epsilon be positive. Okay. Now we say, so we have given this uniformity. So let's uh, so what does this mean? Let me write it down here only. This uniformity gives us that if you start with any epsilon greater than 0, then there exists n in natural numbers such that fnx minus fx is smaller than epsilon for all n greater than equal to n. Okay. So yeah. So I will take yeah. So I will apply this uniformity definition. Okay. I will apply this uniformity definition uh, for epsilon to be epsilon prime to be epsilon by b minus a. Okay, where this epsilon is coming from this epsilon. Okay, so I'm starting with an epsilon over there, and I'm taking a new epsilon prime, okay, and finding out the corresponding n. So this is n epsilon prime in natural number such that fn minus f is smaller than epsilon prime, which is epsilon by b minus a. Okay, so we will see why I'm doing this. Okay, so if I take let epsilon be positive, okay, number, we choose n to be this n epsilon prime in natural number. Okay, okay, now consider for the case when n is greater than n epsilon prime. So what do we have here is this difference, modulus of this difference. Okay, so now this is equal to, considering the integration of this particular function, and now this is further smaller than integrating the modulus of this function. Okay, so in particular I'm using this fact that integration of f over dx and taking the modulus over after that is smaller than integrating a positive value function over the same uh, domain with the same function. Okay, so using this fact, now what I have this thing in left, that fn minus this, and this was smaller than or equal to, correct. Okay, this is what we have. Sorry, fn minus f dx, correct. Now if f yeah, if integral of, okay, sorry, if f is smaller than some quantity, let's say k, okay, in particular fx is smaller than quantity for all x in ab, if then integral of fx will be smaller than the integral of k, and now since k is constant, so it will be just k times b minus a. So using this second fact, I can further bound. Now what is the bound on the modulus of fn minus f? The bound on fn minus f is by epsilon prime. Okay, so it is by epsilon prime dx, which is this epsilon prime dx is equal to epsilon prime b minus a, which is equal to epsilon by b minus a times b minus a. This b minus a cancels out, so you are left with epsilon. So in particular, what we have proved is, just look at the statement. So I have started for any epsilon, choosing this n, okay, and considering the case when n is small, n is greater than n epsilon prime, I have proved this inequality. So what I have proved, let me write it now. For any epsilon greater than 0, there exists n in natural number such that this quantity is smaller than epsilon for all n greater than n. Okay, so that is what I have proved in particular. Now this is equivalent to say that this fn sequence of this real number converges to this. So this completes the proof of the theorem, proof of the question. Okay. So any doubt in this part? I'll wait for a couple of minutes. Oh, good. Okay. So this statement is true. Okay, now let's move on to question number 6. So in this question, we need to show. So in this question, we need to show that the sequence of f and x uh, converges uniformly to the zero function. Okay. So I'm not going to repeat the definition of the convergence, uniform convergence. Okay. So so in this question, I will use a particular inequality involving this sine function. Okay. What is that inequality? That inequality says that the sine function is bounded above by 1 and bounded below by -1. Okay. All of you are familiar with that inequality. And the idea is to use that inequality to prove that this function is converges uniformly to 0. So this is another example to for another example of uniformly convergent function. Okay, so let's get into that. So the inequality that I'm going to use is this: sine of theta is always smaller than 1 and always larger than -1 for for theta varying from for theta varying in r. Okay, that's the first part. The second part that I'm going to use is that limit of 1 over n square root of n is equal to 0 as n tends to infinity. So these are the two facts that I'm going to use. Okay. Okay. So first, uh, let epsilon be a positive number. Yeah. We need to choose some n epsilon. Okay. So we choose n in natural number such that the limit such that 1 over n, this modulus, is smaller than 0 for all n greater than n. Okay. So I choose my natural number in this way. Now why in this way? Because limit of 1 over n square root as n tends to infinity equal to 0. If I translate it into the epsilon delta definition, what will I get? For any epsilon greater than 0, there exists n in natural numbers such that 1 over n, this is smaller than epsilon. Okay, this is smaller than epsilon. So I'm just only hunting for that epsilon. I'm only hunting for the n. Oh, sorry, this can't be. This is more than epsilon. I wrongly wrote that. Yeah, yeah. So I'm only hunting for n such that n epsilon square root is smaller than epsilon, and anything which will be larger than this capital N will again be smaller than this 1 over n square. Okay, so I'm only hunting for that n. Okay, so this choice is clear now why I'm choosing such an n. And now, uh, okay, now we consider n to be greater than this n, first of all. And now we consider the limit, this difference. Now this difference is what? This is sine n x divided by square root of n minus 0 function, which is 0. So this is going to be equal to sine nx divided by square root of n. Okay. Now I use the triangle now I use the inequality on sine function. Okay. So using this, what will I get is that this quantity, oh, sorry. Yeah, only sine x. Yeah, this quantity is smaller than 1 over square root of n. Correct? And by our construction, this is smaller than epsilon. Okay. So in particular, if I just try to summarize whatever I have done, okay, if I just try to summarize whatever I have done, so I've started, so for any epsilon greater than 0, I have found out uh, the existence of the natural number n such that the fn minus f, which is sine nx, is smaller than epsilon for all n greater than capital N, which is equivalent to prove that fn converges to f uniformly. Okay, so I have proved that fn converges to f, which is a zero function. So fn converges to a zero function uniformly. Any doubt in this question? Okay, good. So now let's move on to this last question of today's discussion. Uh, so this is again a simple question. We all have done this part, but why I am doing this is just to emphasize uh, the geometry behind the critical points. Okay, um, yeah, and that's why I'm working with a simpler dimension r square to r, so that you can, these things can be drawn in R3 spaces. Okay, you can draw the graph of these to see how will it look like. Okay, so um, let me start with part one. Okay, so in part one, my function fxy is given to be x square plus y square. Correct? Yeah, it is given to be x square plus y square. So if I find out the, so in order to find out the critical points, you need to first calculate its partial derivative with respect to each direction. Sorry, with respect to the coordinates direction. That means with respect to x and with respect to y, and then equate those partial differential to 0. So we will get 2x. Okay, and differentiating with respect to y, I get 2y. And if I further equate these to 0 vector, I get x and y to be 0 as the critical point of fxy. Okay, so now it is the critical point of fxy. Now if I further analyze this function, basically if I want to find out the nature of this critical point, so I need to perform the second differentiation operation. So in particular, I need to calculate the Hessian of this function, and if it turns out to be negative, positive, then it will tell us that whether it is um, a maxima or a minima. Yeah. So without going to that, if I try to see this, so at a point of origin, yeah. So at the point of origin, if I try to uh, write the differentials, so in the direction of x, it is, so in this direction, which is the x direction, this is the y direction. So in this direction, it is 2x. Okay. Yeah. So if I perform the double differentiation of on x, I get 2, which is a positive quantity. Okay. And if I calculate the Hessian of this function at 0 comma 0, what do I get? I get, basically I need to find out the determinant of this function, which is determinant of this matrix, which is 2 first, and the second quantity it will be, yeah, it will be 0. Here it will again be 0, it will be 2 again, so it will be 4, which is positive. Okay. So what does it suggest to that? If I use the second derivative test, so it suggests that that 0 comma 0 is minima of f, correct, because the Hessian of f is positive, which implies that it is uh, you can talk about its nature of this critical point. And double derivative is positive, it implies that it is a maxima, sorry, a minima. Okay, now if I try to look it geometrically, so the figure uh, near this critical point, so if you just consider the points that is on the uh, x axis, so so in that case it will be just a x square graph. And how does an x square graph look like? So x square graph look like this. Okay, so this is an x square graph. And similarly, if this is my x-axis and this is a z-axis, z-axis is the one uh, where I'm projecting the image point. Okay, and similarly, if I try to draw the function graph when x equal to 0. Okay, so this is the graph when y is equal to 0. So that means, sorry, so that means it is x comma 0 comma z. Sorry, x comma this. So it is this the graph of this point, which is in x z. Now I'm drawing y comma f 0 comma y. So what will I get? I will get uh, again y square. Okay, it is y square. So you can in 3 dimension, if you try to see this, this will look like, and this is dimension x. So I am taking this x y z. So if I'm looking, if I'm just keeping my z 0, that means I am on xz plane. So it is like this curve, which is x square. And if I am on yz plane, then it is this thing like y square. So it is giving you, and these things are like filled up these things, and it goes throughout this. So in particular, you kind of get a bowl like structure, okay, at origin. So this is origin. So you get something like this kind of figure at origin. Okay, for the, if you try to draw the graph of this function x square plus y square. Okay, so you can see wherever direction you go, you are going to the minimum value point of the function. Okay, and everywhere else it is getting larger and larger values. Okay, so that is the idea to go behind the geometry of this function. Okay, that's what the aim of this question. Now one can perform the similar exercise for number 3 also, for h also. Okay, so similar exercise can be done, and you will get something like minus of x square. If you restrict to, if you take y equal to 0, you get minus of x square, which is like this kind of thing. And if you take x equal to 0, you get graph which is like, which is again like this. Okay, so in particular, so this is your y, this is your z axis, and this is your x axis. So in particular, your graph will look like x y z. So at origin, your function will look like a ball facing towards the ground. Okay, this will be the graph of your function. And the second case, if we understand the second case, so in the second case, what is happening is g of xy is given to be x square minus y square. If you find out its differential with respect to x, you get 2x, and with respect to y, you get 2y. Okay, and if you find out the Hessian of this g, and again the critical point will be origin in this case. Okay, so if you calculate the Hessian at this, which is nothing but the determinant of this thing, you get -4, which is negative, implying that it is a saddle point. Okay, so so a similar observation can also be done in the case of 2. Okay, in the case of G, where you have saddle point. So so this gives you the minima, this gives you the saddle point, and this gives you the maxima. Okay. Okay, so I hope this makes sense to you. Um, I stop now. If you have any question, you can ask me. Okay, if there are no questions, we can stop the recording here. Uh, so we will meet next time Monday. Um, yeah, bye. Bye everyone.